Hi guys, we are continuing solving our task and today we have the following. Lowest common ancestor of binary tree. So we are given binary tree and we have to find the lowest common ancestor of two given nodes in the tree. According to the definition, the law LCA is defined between two nodes, P and Q, as the lowest node in T that has both P and Q as descendants, where we allow a node to be descendant of itself. So we have binary tree, and we have the LCA of node 5, and 5 and 1 is 3. Okay, so here LCA of node 5 and 4 is 5, since a node can be a descendant of itself according to LCA definition. Okay, so once again, we again binary tree finds the lowest common ancestor of two given nodes in the tree. The loss is defined between two nodes. As descendants. Yeah, not sure that I understand. Let's translate. Найнижчий спільний предок. Найнижчі узолти, які мають нащадки. Okay, so we have 3, 5, 1. Why here is 5? Okay, so I try to understand this. I'm not sure yet. Let's maybe read some comments. Two given nodes in the tree, so the param P and Q are node reference in the tree. Use Okay, so here 3 is ancestor of 5 and 1. But here is also can be. Yeah, okay, so we are given a tree and also we have P and Q. Okay, so we have node P and Q, 5 and 1. And we have to find their own close ancestor. Okay, now I understand. So now we are given 5 and 4, and we see that 2 is not the common, so I need to yeah, what I need to do actually is, so I'm given 5 and 4. So when I start from 3, I find 5, and I know all its parents. Then I iterate over 4 and also find all its passes. So I have like 2 passes, and yeah, and then what can I do is to check if I have some value in this pass. So I can have like 5 or 4 in the pass. And if I have this value in the pass, then just return this tree node. Yes. So just return this tree node. Okay, so what else? How also I can do this? Let's check. So another way I can iterate. So when I find some node P, for example, and I return, and then I find Q, and I also return, and try to find its common ancestor. So for example, I can go by tree doing like DFS. And first I try to find P. So for example, I have P first, it's 4. So I'm going here. Then when I found P somewhere in this position, I try to find Q. Q, let's say 5. And see, yeah, so when I found this balls, I found this one and I found this one. I go up to the previous 2. So maybe a DFS and maybe like a stack. I can put elements in stack. Yeah, I think that first of all, I can check for P if I have P in, like in the bottom, and Q if I have Q in the bottom, and check it's this edge case actually. If it's not, then I should find this this situation. Yeah. So first traversal, second traversal, and third traversal, it would be yeah. So it would be when I go find first, then find second, and then go up by them. But how can go up? Yeah, by visited. Okay. So I think that I understand. So the solution is the following. So first, we check edge cases when one is parent of another. And the second approach is we collect to the set. We collect to the set. We collect nodes to the set. So first of all, we are going and collect each node to the set. How many nodes can we have? Node values. Oh, 10. Okay, so I have 100,000 nodes. Yeah, it's quite a lot. Can have like memory issue here. Okay, how much time do I have? 15. Okay, so I have like 10 minutes. Okay, so let's try very quickly. So first I start with P, right? And trying to find Q. So I'm doing like DFS, start with current node and find PQ. And here here I just return P result. And this DFS would look like this. So we have DFS where we have denote current and find. If our current equals to null, then we just return null. If our current is equal to find, we return current. Here we do like DFS for current left and find tree node left. Here right. And yeah, so in this situation we check yeah, so we check if left is equal to null, then we return right, otherwise we return left. Okay, so here we do Q, and here we Q, Q, P. And if P are not equal to null, we return PR, and the same for PQ, QR. Okay, and now we are doing this one. So how we are doing this? So first we try to find P and add in all these elements to the set. Then we try to find Q, and when we found the Q, we are yeah, so when we add to Q, we are, so we have values more than, okay, so it's not unique. Not all nodes are unique. Okay. Okay, then it's good as well. So we can have like set of, or even map. Yeah, so we can have like a map of integer and tree node. We can have this map. Then we can have a find function where we pass our root and P. So the idea of this find function is to populate this map. So we have our tree node, and this PC. What is this? Yeah, so we have this tree node P. And if our root is equal to P, then we just return. Then we make like find for root left and P, root right. So here we actually found our, somewhere here we found our root. So for example, we go left and we found our root, so we return back. Then we go right, We didn't find it, so we again, we go right, then left. Okay. So we have set 3 nodes. Probably set would be enough, maybe. Yeah, so we have set, then it will be set. We are passing this set here, and yeah, so we are adding this set here, and when we found our root, so we are going here, we found it, right? We found our root and we going back. So let's say 5. So on the left, found, go back. Now we here. So when I think we should do something here, and when root is equal null, we just return null. Yeah, we return null, otherwise we return the set. Yeah, we return set. Here it will be return set, and here it will be always new, like set at root, and here it will be new set of this set. Here to the right, left, and as well return right not equal to null. Then we return right, otherwise left. Okay, so we have this find function where we found our set. So let's print, let's return null and print this, how it works. Pass. Here will be our pass. Let's go. Okay, so yeah, it's a problem. It's a problem. Let's maybe then just print here 3 node and plus here we just print and wow, or something like this. Let's go. 3. Yeah, actually it's correct. For this one, 4. 4. Output 4. 5, 4. PQ. Yes. So when we go from P to Q, so P is 5, and we trying to find 4. So, and we call this DFS current. Yeah, and yeah. So when we found it actually, and we return it from DFS. So yeah, so here we can actually return P. Here we can return Q. Yeah, so this works. Now, when I have this find, I can like make find 2. So how it would work with find 2? I have my find. I have my 2. I have my root. I have my set plus, and I have my Q. And to return from here. So Q. How it will work? So when I find my Q, yeah. So when I found my Q, I have to return what I have to return. Probably Q. Right. And here I call something like this. Three node, and if yeah, so for example here I found 3, right? So when I found my node, I check if set contains node, I return node. Then another. Yeah, but it will not. Yeah, okay. So it's already 30 minutes. So I think that I will stop here. Let's check solutions. Yes. So if I found P or Q, I just return this note. Then I returned right. And if left and right is not equal to null, okay. So for example, so if I check this example, I first found 5, then I go to right. But what if I have on the left this value? So yeah, so here I found left, right? And yeah, trying to find on the right, but it's not there. So if left not null, then I just return left. Ah, okay, yeah, that's one. It's interesting. And if right and left not equal to 1, then return root. Yeah, it's interesting. Thank you.